So in previous lessons, we've learned how to solve systems of equations using the elimination method, the substitution method, and most recently, how we can use matrices and use Gaussian elimination, which is row reducing, to get to a particular format and then we can see our solution. There's another way to solve systems of linear equations, and that's using inverse matrices. And that's going to be our goal in this class, to see how can we solve a systems of equations using inverse matrices. But first, let's introduce what an inverse matrix is. To begin, we're going to learn how to multiply matrices. Now, one thing that's important is whenever you multiply numbers, 3 times 2 is equal to 2 times 3. The order doesn't matter. But when it comes to multiplying matrices, A times B is not necessarily equal to B times A. So we'll want to remember when we multiply matrices, order matters. Here we're asked to multiply matrix A and matrix B. Now, in our last lesson we saw augmented matrices which had a vertical line to represent what they're equal to. In this case, since the vertical line is missing, this is just a regular matrix where we have 2 rows and 2 columns. So we would read 5 as the first row, second column entry. And when you multiply matrices, you go through this process. You write it out in the right order, so A comes first because it's A times B, times and then there's a process we're going to want to visualize. The process that you visualize is when you're multiplying matrices, you always start with the first column in the second matrix. So visualize this. And what we're going to do is we're going to imagine grabbing this and then lifting and turning it to where it's sitting right above the first row. So I would visualize here in my mind a 3 and a -2. So it's like we lift it and then turn it 90 degrees and it lines up here. So 3 goes here, -2 goes to the second row. And then what we're going to imagine, what happens next, is imagine bringing this down to the first row, and then you multiply and add the terms. So you multiply 3 times 1 plus -2 times 5. So we'd say 3 times the entry 1 plus -2 times 5, whatever that is, becomes the entry in the first row, first column. And then what you do is you continue that multiplication down through all the possible rows. So we just multiplied to the first row, so now we multiply down to the second row, which means we take a 3 times a -2 plus -2 times -9. And you do that where you multiply this through all the rows, and when you've multiplied it through all the rows, you're done using that. And then the process continues where we pick the first column, now we pick the second column, and we do the same process. So now I visualize taking this column, lifting it and turning it to where it sits right over the first matrix. So that would leave me with a 4 here, a 5 here, and now I take this and I multiply it by the second row, which would give 4 times -2 plus 5 times -9. And since I've now multiplied this by all the possible rows in the matrix, and I've used up the last column, you're done. There's nothing else to do, so then you close the matrix. And we'll be finished whenever I simplify these multiplications and sums. So let's simplify that. That would give us 3 times 1 is 3, plus a -10. The second row, first column would give me a -6 plus 18, 4 plus 25, -8 minus 45, that would give me -7, 12, 29, -7, 29, 12, and -53. So that is what is A times B as a matrix. Now there's a pattern in what will be the size of the resulting matrix when you multiply 2. So we would call this matrix, since it has 2 rows and 2 columns, we would call this a 2 by 2. And we always describe the size of a matrix by the number of rows, and then we write this by symbol, just an X, number of columns. So in this case, A times B is a 2 row by 2 column. And if you know the size of the matrices that you're multiplying, you can know the size of the resulting matrix, and that can be a way that you check your work. So here's the rule. If you multiply matrices, you can only multiply them if the number of columns in the first matrix matches the number of rows in the second matrix. So for instance, here is our first matrix. It is a A by B. Our second matrix is a B by C. Since they share this value, they can be multiplied. If they didn't share that, they couldn't be multiplied. And the result is a by C. So you can know the resulting multiplied matrix will take the number of rows of the first one and the number of columns of the second one. So let's use this to identify if we can multiply certain size matrices. So here we have 4 possible matrix multiplications. And take a moment to identify which of these fits our rule here, that only these type of matrices can be multiplied. And I recommend you pause the video, inspect these, and then circle the ones that can be multiplied by our matrix multiplication rule. And then unpause to check your work. Now we know only matrices that share the same interior value when we look at them like this can be multiplied. So these can't be multiplied because it's a 1 and a 5. These can be multiplied because the interior is both 1. As can these, because they're both 3. But these cannot because they're different. And we even know what the resulting size would be. The resulting size of this one, think about it as if the 3's cancel and that just collapses to give us a 2 by 7. And the resulting one here, imagine the 1's kind of collapse and that leaves us with a 3 by 5. So always when you're asked to multiply matrices, verify that the rows and columns line up and fit this rule. Now that we know how to multiply matrices, we're going to talk about what makes a matrix an inverse matrix. The way we represent inverse matrix is if we have matrix A, then we call its inverse A, and then we rise a superscript to the -1. So this is the inverse matrix. This is the matrix A inverse. And the property of an inverse matrix is if you take the original matrix and you multiply it by its inverse, you should get what's called the identity matrix, which we're going to describe shortly. And similarly, we know order of multiplication can matter in terms of matrices, so this was A times A inverse. The result holds if we take A inverse times A, we should still get back the identity. And the identity matrix depends on the size of the matrix. For 2 by 2 matrices, the identity matrix is 1, 0, 0, 1. The identity matrix is always going to have 1s on the diagonal, 0s everywhere else. For 3 by 3 matrices, the identity matrix, since there's 3 rows and 3 columns, would be 1, 0, 0, 0, 1, 0, 0, 0, 1. Again, visually we see that on the diagonal there's 1s and there's 0s everywhere else. And we could extrapolate that out to 4 by 4s, 5 by 5s, but we're not going to see anything larger than a 3 by 3 in this class. Now, the interesting property about the identity matrix is that if you take the identity matrix and multiply it by any other matrix in either direction, you just get back where you started. It doesn't change things. Let's verify this for ourselves. We're going to take A, and we're going to multiply it by the identity. Since it's a 2 by 2, I'm going to multiply it by the 2 by 2 identity. And we know our process for multiplying these is we're going to take the first column of the second matrix, start here, and we're going to imagine that we're going to lift and turn it and line up the entries over here. So we're going to visualize a 1 and a 0. And then we take this row and we multiply it by this. Write that down. Then we take this row and multiply it by this, and then since we've done all the rows, we go to the next column. So this will be a 1 times 3 plus 0 times 4. Now that we finished that row, we take this and multiply it by the second row. That would give me a 1 times negative 2, 0 times 5. And since this is multiplied by both rows and there's no more rows to multiply by, we then imagine taking the next column over and doing the same thing. So we take this, imagine rotating it and lining it up here. That would give us a 0, 1. And we multiply through each of the rows. So times the first row would give us 0 times 3 plus 1 times 4. Multiply it by the second row now. That gives us 0 times negative 2, 1 times 5. And since it has these zeros, what it does is it cancels off the second term and you just are evaluating what you started with, which is why we get to stay wherever we began when we multiply by the identity. So we get 3, negative 2, 4, 5. So indeed, A times the identity just gives us A back as a result. Now for practice, take a moment to verify for yourself that the identity times A would still give me A. So here I'm reversing the order of multiplication. So now I'm going to take these columns and bring them over and multiply them by the rows in that pattern. So why don't you pause the video, multiply these, and verify that you would still get A in this case as a result. After multiplying, we would get the same thing. We would get 3 times 1 plus negative 2 times 0, 3 times 0 plus 1, negative 2 times 1, 4 times 1 plus 5 times 0, 4 times 0 plus 5 times 1, and all of that simplifies to 3, negative 2, 4, 5, which is exactly A. So remember, the identity matrix times any other square matrix is just the original matrix. It's the equivalent to multiplying 1 for matrices.
As we reviewed the idea of the identity matrix, we're about to see when two matrices are inverses. Before we look at that, I'd like to review back to our definition. We said that A times A inverse would equal the identity. And this is the exact criteria for when two matrices are inverses. Two matrices are inverses if when you multiply them together through matrix multiplication like we just practiced, you would get back the identity matrix. So for our next example, we're asked to show that these two matrices are multiplicative inverses. And the way we're going to do that is we're going to remember A times A inverse equals the identity. So if they are inverses, we should be able to multiply them and get the identity back as a result. And if we looked at that formula, the order that we multiplied them in this case did not matter, which is an exception because in general the order of matrix multiplication matters, but with inverses it doesn't. You could take one times the other, you're still going to get the identity. So in this case, let's start A times B. Remember, you write A first. And we're following the same procedure of matrix multiplication. We just have to remember the pattern. Remember, the pattern is that you take the column, the first column of the second matrix, visualize this, and then imagine lifting it and turning it, and it lines up with the rows above. And if you need to, you can write in the values and just erase it, so -9 and then 2. So now that we visualize taking that and turning it, we are then going to multiply each entry by each entry, so -9 times 1 plus 2 times 5. That's what goes in the first row, first column. And if you're confident, feel free to just do this matrix or this multiplication and addition in your head, or you can write it out step by step like I'm doing. And then we take that and we do the same procedure for every row there is in the matrix. So we already did the first one, so we're going to do the second one. That would be -9 times -2 plus 2 times -9. So we've done that for every row of the original matrix. So then we get the next column. So erase that and visualize taking the next column over and doing the same thing. Lift and turn. Rewrite if needed. So that would be a -5 and a 1. And then we imagine taking this and multiplying it by each of the rows. So that would be -5 times 1 plus 1 times 5. And we do that for every row in the first matrix. So take that now towards the second row. -5 times -2, 1 times -9. And then after we've done the matrix multiplication, the last column has been multiplied by both of the rows. There's nothing else to do, so we close off the matrix. And as expected, remember, we can know the size of the resulting matrix from matrix multiplication. This was a 2-row, 2-column, a 2 by 2, times another 2-row, 2-column, 2 by 2. The middle terms, we imagine them canceling, and that means our resulting matrix is a 2 by 2, which we see here. We just have to simplify the interior. That's a -9 plus 10 is the first entry, a +18 plus a -18 for the second entry on the first column. Then we've got a -5 plus 5 and a +10 minus 9. Now that simplifies to be 1, 0, 0, 1, which is the identity matrix. So this tells us that A and B are inverses of each other. So if you're ever asked to show that two matrices are inverses, you're just going to multiply them, and if you get the identity, they're inverses. Now for practice, why don't you take a moment to pause the video and next multiply B times A. Now we're going to expect the same result. We should get the identity since we know these are inverses. But for practice of matrix multiplication, go through the process yourself and identify that, or determine that if we reverse the order of multiplication, if we now take matrix B first, multiply by matrix A, we're still going to get the identity. So I recommend you pause the video now, attempt this on your own, unpause to check your work. So through our process of matrix multiplication, we would get 1 times -9, following our process as before, plus -2 times -5. Then we would get 1 times 2 plus -2 times 1. Going now to our second row that we're bringing over and multiplying, we would get 5 times -9 plus -9 times -5. Then we would get 5 times 2 plus -9 times 1. Simplifying these, this is -9 plus a positive 10 would simplify to be a 1. Positive 2 plus -2 would be 0. -45 plus positive 45 is 0. 10 plus -9 is 1. And we verified that these are identities again. So we've introduced the idea of an identity matrix and an inverse matrix. And we've shown how to, if you're given two matrices, verify that they're inverses. You would multiply them and see if you get the identity back. But how do we go about the process finding the inverse of a matrix we already have? Okay. These are not necessarily exactly the same things, but you can kind of think of this as the same category of I give you a function, find the inverse function. Now we're giving you a matrix and you need to find the inverse matrix. And for a 2 by 2 matrix, remember I call this a 2 by 2 matrix because there's 2 rows by 2 columns. For a 2 by 2 matrix, there's going to be 2 methods that we're going to use, and we'll outline both methods for the same problem here. And you can choose whichever one you prefer to work with. So watch both explanations and be trying to identify which one you would prefer, and then use that for your future homework problems. I'm going to illustrate the first method. So remember, this is option 1. The first method is to do row reduction similar to what we did in our last section when we were solving systems of equations. Except instead of a system of equations, what we're going to try to do is you take the matrix that you start with, in this case 2, 1, 5, 3, and you draw your vertical line, and what you put next to it is the corresponding identity matrix. So in this case, this is a 2 by 2, so its identity is 1, 0, 0, 1. And then you close the matrix. And the goal is to, by the end of all of our operations, we're going to do a lot of row operations, and at the very end, our goal is to have, on the left side, we're going to transform this matrix into the identity, and then on the right, we're going to keep track of what numbers these become, and then whatever becomes on the right of the vertical line, this is our inverse matrix, whatever we find here. So the goal is to make this look like the identity through row operations. As we do that, if we're careful, and we treat this as one row, another row, as we're manipulating the left side, these values are going to change and keep track of those changes. And at the very end, whenever this left side looks like the identity, then this right side is going to be exactly the inverse. So we have to stay focused on our goal, and eventually we'll get our answer. So remember, our goal here is to get a 1 first in the upper corner, and we work here. We go this first, and then this, and then this. Work in a U shape. We currently would like this to be a 1. It's a 2. So remember, you can multiply to make things different values so long as you're not trying to get a 0 there. So I could multiply the entire first row by 1/2, and that would change my first entry into a 1. So with row operations, we write out what we're doing to help us remember. 1/2 times row 1 is going to be the new row 1. Everything in the first row gets multiplied by 1/2, so I get a 1, a 0.5, a 0.5. 1/2 times 0 is still 0. Row 2 stays the same. Okay, we stay focused. We now have our first piece met. We've got this done. Next, we focus on the fact that we'd like this to be a 0. Remember, the only way you can get zeros is by multiplying another row by a certain scalar and adding it to the row that you want to have a 0 in such a way that they would cancel and give us 0. So the only thing that I can add to 5 and get 0 is negative 5. So I want this row to have a negative 5 here so that when I add them, they would cancel and give me a 0 here in its place. So to do that, I'm going to say negative 5 times row 1 is the new row 1. So that would be negative 5 times 0.5 is negative 2.5, negative 2.50. And we leave the other one the same. And at this point, our whole goal was to add these so that the 5 would cancel in the second row. So now we're going to say row 1 plus row 2. That's going to be the new row 2. So we take each piece at a time. Negative 5 times 5 would give us a 0 in its place. Negative 2.5 plus 3 is negative 0.5, or sorry, positive 0.5. Negative 2.5 plus 0 is negative 2.5. 0 plus 1 is 1. And then remember that we only changed row 1 in order to add these. Now that we've added it, we go back to the original row 1 that had the 1 in the right place that we wanted. Okay, always watch for copying errors that could throw us off. We now have the 0 where we want, so next we know we're going to try to make this into a 1. You can get a 1 by multiplying by a correctly chosen value. Think, what times 0.5 would give us 1? 2. So if I take the entire second row and I multiply it by 2, that's going to be my new row 2. Zero times 2 is 0. 2 times 0.5 is 1. 2 times negative 2.5 is negative 5. 2 times 1 is 2. Okay, so we now have our 0 in this location, or our 1 in this location. The last thing is we want the 0 in the last quadrant, which is right there. We know to get 0, I have to somehow fix one of the other rows to be the exact opposite value in that location so that I can add them. So I want there to be an opposite value to 0.5, so I want a negative 0.5. So I'm going to multiply this one whole row by negative 0.5 so that I can then add the rows and that will cancel. So we write out our goal. Negative 0.5 times row 2 is the new row 2. We're only doing this so that we can add it later to the other term. And we would get 0 times negative 0.5 is still 0. 1 times negative 0.5 is negative 0.5. Negative 0.5 times negative 5 is a positive 2.5. Negative 0.5 times 2 is a negative 1. And then we leave the other one unchanged. And at this point, our goal was to get the 0 here. So we add row 1 plus row 2. And that's going to be the new row 1. Give everybody a moment to write that in on their paper. Add them together. Remember, term by term, 0 plus 1 leaves us with 1. 0.5 plus negative 0.5 gives us 0. 0.5 plus 2.5 gives us positive 3. 0 plus negative 1 gives us negative 1. And then, remember, we only change this to add, which we've already done, so we go back to the original row 2 that we liked, because it had the 0 and 1 that we were looking for, and we just copy that here. And once we've met our goal, we've got the entire left side looking like the identity. Then if we've kept track of the changes correctly and treated these rows as we've done, then this is exactly the inverse matrix. So it's called A, so its inverse would be called A inverse as a superscript. And that's the matrix 3, -5, -1, 2. Let's take a moment just to verify that for ourselves. So remember, if these are inverses, then we should be able to multiply them and get the identity back in whichever order. So 2, 1, 5, 3. Take a moment and multiply that by 3, -1, -5, 2. And see if you get the identity back as a result. This would be a good time to pause, work this out, and then unpause to check your answer. So as we multiply these, I would get 3 times 2 is 6, plus -5 is +1. 3 times 5 is 15, minus 15 is 0, if you go through the matrix multiplication. -1 times 2 is -2, plus a +2 would give me 0. -1 times 5 is -5, plus 6 gives me 1. So indeed, when we go through matrix multiplication, we do get the identity. Since y'all worked that out, I did the shortcut, but y'all can verify that that works through our matrix multiplication procedure. So we're confident that we got the identities. Now this was option 1. Remember, you write the original matrix, next to it you write the identity, and the goal is to turn this through row operations into the identity, and then the resulting matrix is the inverse. Let's discuss option 2, and then we'll come back to this example, do it again using option 2, and y'all can decide what you prefer as a method going forward. So option 2 is to use a formula. Now this formula works whenever we have a 2 by 2 matrix. Let's suppose that we have a matrix A, B, C, D. So it's a 2 by 2, and the first row, first entry in the first column is A, first column, second row is C, first row, second column is B, second row, second column is D. Then A inverse would always follow this formula. It's going to be whatever this number is, which is 1, all divided by AD minus BC, that's the pattern there, multiplied by the matrix where we've switched a few things. On the main diagonal, we reverse it, so instead of AD, it's now DA. And on the off diagonal, we just apply a negative sign. So whatever was positive originally becomes negative, whatever was negative originally becomes positive. And that's the way you can find the inverse matrix. Now, if when you try to calculate AD minus BC, which is what goes here, if you get 0, what that means is the matrix has no inverse matrix. Let's go back to our previous example and work this with this second way of finding the inverse. So our original matrix was A is 2, 1, 5, 3 from this example. So option 2 is to say that, okay, A inverse then is going to be 1 over some number times the pattern. Now what's the pattern? The pattern is that you switch the order of the main diagonal, so instead of 2 and then 3, we're going to have 3 and then 2. On the off diagonal, you change the sign, so it was currently a 1 and a 5. We're now going to have a -1 and a -5. And then you multiply by a scalar. What's the scalar? It's found by taking the main diagonal, AD, minus BC. So that's 2 times 3 is 6, minus 1 times 5 is 5, so 6 minus 5 is 1. And that would give us exactly 1 over 6 minus 5 times this matrix. But 6 minus 5 is 1, so that's just 1 times the matrix. And whenever we take a scalar times a matrix, what that means is you take the scalar and you multiply it by every entry, but everything times 1 is just itself. So no surprise, we get 3, -5, -1, and 2. And we would find the exact same inverse matrix as before, because we're doing the same problem, just 2 different methods, so we should expect the same answers. Now I think from this we'd agree that option 2 is a lot faster. But it's still important to know how option 1 works, particularly whenever we'd like to look at a matrix of a 3 by 3. Because we have this nice formula for a 2 by 2, but we don't have as nice of a formula for a 3 by 3 inverse matrix. So let's practice this again. You're asked to find this inverse matrix, and you can either use the formula or the row reducing method that we saw in option 1. Whichever method you choose, I recommend you pause the video, work and find the inverse, multiply the inverse you found times the original to verify that they are inverses, and then unpause to check your work. Now I'm going to solve this using the formula because it is very efficient. So if this is my 2 by 2 regular matrix, then A inverse is guaranteed to be to 1 over something times the original matrix moved around a bit. Now I know that I switched the main diagonal, so instead of 1, negative 3, I'll have negative 3, 1. And I know the other diagonal, I switched the signs. So 4 was positive, so it becomes negative. Negative 1 was negative, it becomes positive. And then we multiply by 1 over AD minus BC. So 1 times negative 3 minus 4 times negative 1. Now that can simplify. 1 over negative 3 minus a negative would become a positive, so plus 4. So that would just give us a 1. Now multiplying by 1 doesn't change anything, but remember, if this is a value that's not 1, then you could either leave it outside or you could take it and multiply it by each of the terms of the matrix. So this is our A inverse, and we can verify that it's A inverse by taking the original, multiplying it by our supposed inverse, and we should expect the identity back as a result. We multiply the matrices, take the first column, turn it over, and multiply. That would give us negative 3 times 1 plus 4, times 1 plus 1 times 4. Next, negative 3 times negative 1 plus 1 times negative 3. Take the next column, bring that over. Negative 4 times 1 plus 1 times 4. Negative 4 times negative 1 plus 1 times negative 3. And now we simplify this. Negative 3 plus 4, 3 minus 3, negative 4 plus 4, 4 minus 3. And that would simplify nicely to the identity 1, 0, 0, 1. And that verifies for us that they are inverses, so we did find our exact right answer. Now we definitely saw that the second method for using the formula was much better or much preferred for finding the inverse of a 2 by 2 matrix. It was still important to introduce how to find the inverse of a 2 by 2 matrix using matrix operations, because that's what we're going to need to do if we're asked to find the inverse of a 3 by 3. While there is a formula for this, it's very complex, so it's not going to be as useful as just going through the matrix operation. So in this case, we write down the exact matrix we started with. And then we write next to it the identity. Now this is a 3 by 3, so the identity is 1, 0, 0, 0, 1, 0, 0, 0, 1. Remember, there's a nice pattern. There should be 1s on the diagonal. And our goal, through a lot of steps, is to eventually get down to the identity on the left side And as we were doing that, then the values over here changed, and we kept track of those changes. And that resulting matrix on the right is the identity. Now we know if we're trying to get the identity matrix through row operations for the 3 by 3, remembering back to last section, then the pattern is you go down the first row, and then you go down the second, starting at the 1, going down. Then you start here and you go up, and then finally you go over. So we're going to change this one first, then this, then this, then this, then this, then this, and then finally that's the last one. And we know this order is important because if we don't go in this order, we're going to keep undoing what we had just done. So do stay to the right order. Keeping that in mind, we know we want the first row, first column to be a 1. And we look, none of the first column entries are 1 already. One thing we could do is I could multiply everything by 1/2 here and I get a 1. But let's try a different method. Would you agree that if I take row 2 and I subtract from it row 1, that would involve taking 3 minus 2, which would give me 1. If I make that the new row 1, then I'll get the 1 there and I don't even have to introduce a fraction of a half. Let me write out what we're going to do then. We're going to take row 2 and subtract it from row 1, and that's going to be the new row 1. And then the original row 2, we're going to just make that, or the original row 1 is going to be the new row 2. Row 3 is unchanged. So let's write down the things that are not changing. Okay, this whole row becomes the second one. The reason it becomes second is I'm subtracting it, so I'm already using the row 2 as my starting point to be the new row 1. So then this should go down to its place. And now for row 1, we are taking the original row 2 minus the row 1 at each point, so 3 minus 2, that's going to give me 1. 3 minus 3 would give me 0. 1 minus 1 gives me 0 nicely. Continuing, 0 minus 1 would give me a negative 1. 1 minus 0 gives me 1. 0 minus 0 is 0. So that's great. All we were trying to do was fix this, but nicely for us, do we see we also got these 2 zeros as well, which is what we wanted eventually anyways. So that was a very nice manipulation. It worked out very quickly there. So you also could have done like what we said before. You could have multiplied row 1 by 1/2. That would work, but as we saw here, this established a lot more at once. So sometimes there are faster methods, and this is one of them in this particular case. Next, we've got our 1 there, so I'm just going to highlight this is done. So next I'm focusing on this should be a 0. It's currently a 2. Now, while I could multiply this one by a negative 2 and then add them, let's still think creatively. What if I took this here and I subtracted this? Then it would be, let's take the second row, leave it alone, and subtract the third row. 2 minus 2 is 0. 3 minus 4 is negative 1. 1 minus 1 is 0. 1 minus 0 is 1. And so on like that. So instead of manipulating 1 and then adding them, in this case, since either is the same, if we subtract them, we'll get our 0 that we're looking for. So this is different than how I've been doing some of the previous examples, and this is just illustrating another way that you can think about it. So let's take our row 2 and subtract row 3. That's the new row 3. Sorry, that's the new row 2. And row 1 and row 2 are unchanged, and row 3 are unchanged, so I'm going to write them down. Row 3 is unchanged. So this minus this, 2 minus 2 is 0. 3 minus 4 is negative 1. 1 minus 1 is 0. 1 minus 0 is 1. 0 minus 0 is 1 is 0. 0 minus 1 is negative 1. Okay, so making progress, we now have this to be a 0, which is what we wanted all along. Now to get this to be a 0, this is our next goal. I can't do a fancy subtraction since there's no other 2's around. So at this point, I'll have to go to my old standby where I'm going to manipulate this one to make it the opposite value so that when I subtract them, I'll get 0. So I currently have a 2 here. That means I'm going to want a negative 2 here. So I'm going to multiply all of row 1 by negative 2. And that would give me negative 2 times each entry is a negative 2. 0 times negative 2 is 0. Negative 2 times negative 1 is 2. Negative 2 times positive 1 is negative 2. 0 times negative 2 is 0. The others remain unchanged. And then at this point, I'm going to take the row 1 plus row 3. And that's going to be the new row 3. And my whole goal in this is to get a 0 in the last coordinate here. Negative 2 plus 2 is 0. 0 plus 4 is 4. 0 plus 1 is 1. 2 plus 0 is 2. Negative 2 plus 0 is negative 2. 0 plus 1 is 1. Second entry stays the exact same. And then remember, we really did not want the negative 2 here long term. That was just to add, which we've already done. So we go back to the original row 1. Let's keep track of where we're at. We now have the 0 here, so we next turn to make this a positive 1. And that one's simple enough. It's currently negative 1, so to make it positive 1, we'll multiply all of row 2 by negative 1. That's our new row 2. 0 times negative 1 is 0. Negative 1 times negative 1 is positive 1. 0 times negative 1 is 0. 1 times negative 1 is negative 1. 0 times negative 1 is 0. Negative 1 times negative 1 is positive 1. The others remain the same. Okay, great. We have now completed this step. So next we want this to be a 0. It's currently a 4, so I'm going to have to get the opposite value here and then add. So remember, in this case, you want to use, since we've got a 0 here, you want to use the other row that also has a 0 there, so that whenever we add them, that stays 0. So we're going to be manipulating this one so that we can add to the third row and cancel that 4. If we want to cancel the 4, we need to add a negative 4. So that means let's multiply row 2 by negative 4. That's the new row 2. 0, negative 4, 0, 4, 0, negative 4. And I highly recommend you write out your steps like I've shown here. You need to be able to write out what you're doing, because if you can make sense of it in your mind and give words to it, you know the patterns that you're going through. So we take the row 2 plus row 3, and that's going to be the new row 3. Zero plus 0 is 0. Negative 4 plus positive 4 is 0. 0 plus 1 is 1. Positive 4 plus 2 is 6. 0 plus negative 2 is negative 2. Negative 4 plus 1 is 3. And then remember, we only changed row 2 to add, which we've already done, so let's go back to our original row 2. 0, 1, 0, negative 1, 0, 1. And at this point, our whole goal was to get the 0 here, but in the process, unexpectedly, we also got this to be a 1, this to be a 0, this to be a 0, this to be a 0, so we happen to be done at this point. No other work needs to be done, so that means this should be our A inverse if we did all the steps correctly. So that means A inverse is the matrix negative 1, 1, 0, negative 1, 0, 1, 6, negative 2, 3. And the good news is you can verify that this is indeed the identity. Remember, we can take the original matrix and multiply it by our supposed inverse, and we should get the identity back as the result. And here I just recognized an negative 4 plus 1 at this step should have been a negative 3, and I wrote it as a positive 3. So that should be negative 3, which would make that a negative 3, and this a negative 3. And with that important correction, that would be our inverse here. So that was just an addition error. Negative 4 plus 1 would give me negative 3 there. And if you go through the process of matrix multiplication, you can follow our similar procedures down each of the rows. Then indeed you would get our identity back. So we verified that these are inverses. And this is our exact answer that we're looking for. So far in this lecture, we have introduced what are inverse matrices, how do you find them, how can you verify their inverse matrices, and now let's get to the point. How can these inverse matrices help us solve systems of equations? In our last lesson, you saw how matrices can help you solve systems of equations, and there's another way using inverse matrices. The way we're working at this is if we've got a matrix A, what we're imagining we're doing is we're multiplying it by some coefficient matrix X to get our answer B. So for instance, if I had the system of equations that would translate to the matrix A being, okay, it's the X coefficients in the first column, so a 1 and then a 2, the Y coefficients in the second column, 1, 0. Matrix X is just the coefficient matrix X, Y. And then B in this case would be what it's equal to, 2, 6. And notice that in each case, the first row corresponds to the first equation. Second row corresponds to second equation. And by this procedure then, if you take matrix A and you multiply it mentally by the coefficient matrix, you would get B back as a result. And the reason that is true is because, remember, take the column of the second matrix, lift and turn it. That's saying 1x plus 1y would have to be equal to the first row entry of 2. Now take that to the second row. 2x plus 0y equals 6. So understanding matrices in these ways, we can see how you could write any system of equations as a matrix equation. That's what we've done here. So right now, hopefully what we're seeing here is this translation between a system of equations and a matrix equation. A and B are matrices. Now keeping that in mind, if we want to solve this system of equations, we know in the end your answer would be x equals y equals some number. But what that's really looking for is, what is this coefficient matrix x equal to? If we knew that, then that's solving the equation. So here comes how inverse matrices work. It just so happens that just like any other equation, if I do something to one side, I'd have to do it to the other side. So if I multiply the left side by A inverse, I'd also have to multiply the right side by A inverse. And remember, this is matrix multiplication. When I do that, A times A inverse by definition is the identity matrix. But the identity matrix times anything should just give you the original thing back as a result. So this should just give me x, the coefficient matrix, xy equals. So this means that you can find what x is equal to, which is what we were looking for all along, by taking the inverse and multiplying it by b, which is the original coefficients. And that's our key idea. This is how you can use inverses to solve systems of equations in a pretty efficient way. Let's see this in one example. So let's use our example that we started with here. We are going to solve this system of equations. And remember, at this point, we're not necessarily learning anything new as an idea. We're just learning a new way to do this, because we already know that we could solve this using substitution, elimination, or Gaussian elimination, which is the matrix row reduction that we saw last section. This is just a different technique. In order to use this technique, I need to know what A inverse is. Well, A is this 2 by 2 matrix, so I know by my inverse property, A inverse is 1 over that special formula where I reduce or I manipulate the terms here. So I switch the main diagonal. I change the signs on the off diagonal. And then I take AD minus BC, so that's 1 times 0 is 0, minus 1 times 2 is negative 2. So A inverse equals 1 over negative 2 times 0, negative 1, negative 2, 1. And the way you would simplify that is, remember, you send this constant multiple through both pieces there. 0 times anything stays 0. Negative 1 times negative 1/2 is a positive 1/2. Negative 1/2 times negative 2 is a positive 1. Negative 1/2 times positive 1 is a negative 0.5. So that's my A inverse. And what this formula tells me is I'll get my solution, which is the xy equals, by taking A inverse, and remember the order matters here, so A inverse is first, and multiplying that by B. B comes from whatever they are equal to in the right order, so 2, 6. And when we do so, we know we take the first column in the second matrix, we lift and turn. So we're going to imagine a 2 here, a 6 here, and we take that and multiply by each row. 2 times 0 plus 6 times 0.5. Take that to the next row. 2 times 1 plus 6 times negative 0.5. Now that can be simplified to 0 plus 3, which is 3. And then 3 plus negative 3, which is, 2 plus negative 3, which is negative 1. And what we can take from that is that x equals 3, y equals negative 1. And indeed, if we verify that, we'll get the right answer, because 3 plus negative 1 is 2. First equation works out. 2 times 3 is 6. So this is our solution to the system of equations, and we were able to quickly find that by first finding the inverse matrix, and then taking that inverse matrix and multiplying what it was supposed to be equal to. The order there matters, and then we got our solution. So if we know how to find the inverse matrix, then we can find the solution to the system of equations using this procedure, which I think is a pretty neat result. So that's it for these notes. Be sure to remember that you're welcome to stop by virtual office hours or send me a Canvas message, and I'll be happy to clarify any questions that you have. Thank you.